Hey guys, we're starting chapter 3, and I am excited. We're doing functions. This is the most important part of math, all of math, functions. Probably one of the most important ideas in the whole world ever developed. It's basically responsible for most of statistics, all of computer science, a lot of physics. It's really allowed people to understand and give them context to understand how things in the world work and how to exploit those things to build a better world. So functions are new. Pretty much through all of history, people just thought about equations, algebraic equations, polynomial equations, like we've been seeing. It wasn't even until 1637 when the idea of a function came about. For context, this is over 2,000 years after the Pythagorean theorem had been discovered. And in 1637, Descartes, who basically invented the graph, introduced the idea of a function, and all he said is that a function is just something that looks like f of x equals x to the n. So you can plug in numbers and then raise it to powers. Now Leibniz, around 1660, gave a stronger definition of a function. He said a function was something you could draw a graph of. So if I just have a graph and I draw something that looks like this, then that's a function, despite it not being a polynomial. And surprisingly, it only took 10 or 15 years after getting the idea of functions down to invent calculus. That's basically because you just had people working without that context. Once they got the context of a function, the math really started flowing. So then 10 or 15 years after the definition of a function like that, Newton and Leibniz both invented calculus. Huge controversy on who invented it first or who did it right. I think it's Newton did it first, but his was unusable. Leibniz did it a year or so later independently, and his is the version we still use today. Then a long time passed, and people were trying to figure out what a function actually is. And in 1825, so it still feels like a long time ago, but it'd be 165 years after Leibniz introduced the definition of a function, and only 195 years before today, Dirichlet, another famous mathematician, presented the modern definition of a function. And the idea is that a function is just a rule that takes objects to other objects. And those objects are called sets, and a function just gives you a way to take in an input and spit out an output. They can be super general. We can look at functions on humans. So we can look at this age function that we'll write from humans into, I guess that would be the whole numbers, which we denote as n. And then you look at something like age of Weston equals 23. So it's as simple as that. You have a function, you put in an input, and it spits out an output. Age of Sadie, my sister, outputs 26. Sorry for a bit of hesitation there. Forgot her age for a second. We can have height as a function of even just objects into the real numbers, where you have the height I guess of looking at objects around me, my iPhone equals, I think it's about 6.2. Again, we can just take the height of Weston, and it will output, I guess that was in inches, so this should output in inches, which would be 69 inches. Even, you can do something more general, like location. So we can take location from objects into what we'll actually call R2. So these are coordinate pairs. And you could look at location of, I don't know, let's just do CU Denver. And excuse me while I get the coordinates for that really quick. Well, Google's not really telling me what it is, but we could output longitude, latitude. And yes, I know I'm spelling it wrong. We could also have another output. We instead could also just have it output as an address. So 1201 Larimer Street. Now, the important thing about these functions is that whenever you put something in, you know how to get an output. So we also have, there are things that are not functions. We can do the same sort of examples, such as age from numbers into humans, where if we did age of 23, is that equal to Weston because I'm 23? Or Brian, one of my friends who's also 23? Or Ellie? There's a lot of different choices. So for that reason, it's not a function because we can't determine what the output has to be. The same thing happens with height, where again, we do height of 69, and that could be Weston. Or it could be Justin Frazier, my high school art teacher, who's also the same height as me. So these are not functions. And don't worry, soon we'll get more rigorous about what are functions and what aren't functions. And it's easier to see when we're actually using mathematics for it. So to define functions, we need three pieces. We need the domain, we need the range, also sometimes known as the codomain, and we need a relation. So typically we can write a function as we did above, where in this case, we have that humans are a domain. The numbers are a range. And then implicitly, age is telling us the relation. And sometimes we'll just, when it's numbers, we typically write out what the relation is. So we could have the function f. Typically we use f for functions. Sometimes G and H because they follow F in the alphabet when we've already used F, H when we've already used G. Mathematicians aren't that creative. So we can take F from, we look at the real numbers, so that's the number line as an output, and we can output we could just say the real numbers again. So this is our domain, and this is our range. And then below we write a rule, f of x, so meaning any number we put in will equal x squared plus 1. All right, I have range and codomain in parentheses. There's a small distinction. So the range is the elements that you actually hit in the set. So for instance, if you have the function f of x equals 1, then the range is only 1 because 1 is everything you hit. Whereas the codomain is the values you're allowed to take on. It's a very small distinction. But yeah, so for now, we're just gonna call it range. And our relation is this right here, where we have f of x equals x squared plus 1. So we would have f of 4 equals 4 squared plus 1. So that's 17. We could have f of the square root of 139, which would be 139 plus 1, or 140. You can do f of 4 plus a, which would be 4 plus a squared plus 1. So now you have a symbol in there, but that's fine. All it's saying is that whatever you have in here for your x better show up in this x right over there. So writing down a function as x squared plus 1 is a fine way to describe a relation, and the most common way that you'll see. Another way to do it is also using charts or ordered pairs. So for a chart, we would look at x alongside f of x, and then just write down where things go. So 1, 2, pi, 5, 7, 15.2, and we just pick wherever we want to send it. 1 can go to 101, 2 can go to 5, pi can go to 6.1, 5 can go to 7, 7 can go also to 7, that's fine. 15.2 can go to 7.1. Now, finding any explicit rule, like f of x equals x squared plus 1, would be difficult with this chart. However, this chart is fine if we just want to, if we only care about these values. So maybe we just want to know what f of 1 plus f of 2 minus f of 3 is. And that's easy. We just look at the chart, look at the corresponding values. We get 101 plus 5 minus, well, I'm sorry, that shouldn't be f of 3. That should be, let's say, f of pi minus 6.1. And that would be 106 minus 6.1, which is 99.9. Maybe take a second to think about why that can't be f of 3. Let's pause the video and think about that. All right, hopefully you concluded that it shouldn't be f of 3 because we never defined where 3 gets sent to. There's actually a whole branch of mathematics, and also works its way into computer science, of what's called interpolation theory, where you find the functions that would best fit your data or whatever you're trying to fill in, based on the function values around it. So if we know what 2 is and we know what pi is, then we can make a guess of what f of 3 should be. We would probably say that because 2 is 5 and pi is 6.1, maybe f of 3 should be 2.7. But that's a different area of math, and we're not going to worry about that right now. But it has really fascinating applications. It shows up in, it's actually how, if you've ever used Adobe Photoshop, maybe you're taking a picture of a landscape and you want it to look all rustic, but the damn electric company put in some telephone lines. They actually have a tool that allows you to erase those telephone lines, and it paints in what it thinks the picture should look like. That's actually an application of guessing what a function should be. One of my friends just recently for his thesis used an algorithm like that as well to help reconstruct 3D MRI data. So it's really a far-reaching concept as well. The next thing we can do to define functions is also just to give a set of ordered pairs. This is basically a chart. We can take this chart and translate into ordered pairs. We do this fancy French brace, and then we can have the pairs 1, 101, 2, 5, pi 6.1, 5, 7, 7, 7, 15.2, comma 7.1, and close it with a fancy brace. And then this is a way to define our function. And given any point, such as any coordinate, such as 7, 7, we read that the input is 7 and the output is also 7. It's important to know how that you can define functions like this. It may show up in some MyMathLab homework. I don't think I will really test you on this way. I think the chart way is a bit smoother and a bit more intuitive. But if this ordered pairs really clicks with you, by all means, go ahead and use it. I fully support it. All right, we'll have more on functions in another video. That's interesting. It seems to not be letting me stop my shit. Huh.